are going over lesson 20 homework sheet. Question number 4. We have the function f of x is equal to x cubed plus 4x squared minus 3x minus 6. What we're going to do is use the rational root theorem to find possible rational roots. And so we will take the factors of the constant, which are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. 1 times 6 is 6, and 2 times 3 is 6. Over the possible factors of the leading coefficient, which in this case is 1. Only one choice. And so my possible factors are positive 1 over 1 or negative 1 over 1, which is negative 1. Positive 2 over 1, negative 2 over 1, positive 3 over 1, negative 3 over 1, positive 6 over 1, and negative 6 over 1. And we will align those from least to greatest, and we will have negative 6, negative 3, negative 2, negative 1, positive 1, positive 2, positive 3, and positive 6. So here is the list of all of the possible real rational roots. Now, what we're going to do is we're going to use synthetic division, and we're going to pick one of those at a time, and we're going to do synthetic division until we get a remainder of 0, and we know that that particular possible root is indeed a root. And so then that's going to bring us down from whatever power we were at to begin with, which is the third power, down to the second power. Okay, so here we go. To do synthetic division, we're going to take our coefficients. The coefficient of x to the third is 1. The coefficient of the x squared term is 4. The coefficient of the x term is negative 3. And the constant is negative 6. And we know had there been something missing, we would have put a 0 as a placeholder. We're going to start choosing possible zeros, and so we're going to choose a 1, and we'll do synthetic division. To do synthetic division, we bring down, and then we multiply. 1 times 1 is 1, and then we add. 4 plus 1 is 5, and then it's back to multiply, add. So now we multiply. 1 times 5 is 5. We add, and we're going to get a positive 2. And then we're going to multiply. 1 times 2 is 2. And then we're going to add, and we're going to get a negative 4. And that doesn't work because we didn't get a 0. It does tell us, though, that the ordered pair 1, negative 4 is a point on the graph, but it didn't give us a 0 of the graph. And so we'll start with another choice. So we will put those leading coefficients back. We just left them. And now we're going to try negative 1. And so we start again with synthetic division. We bring down a 1. And then we multiply. Negative 1 times 1 is negative 1. And then we add, and we're going to get a positive, we add, and we're going to get a positive 3. And then we're going to multiply. Negative 1 times negative 3 is negative 3. And then we're going to add, and we're going to get a negative 6. And then we're going to multiply. Negative 1 times negative 6 is positive 6. And then we add, and we get a 0. And since we got a 0, we know that that is a factor. Now, this excuse me, we know that that is a root. And so if negative 1 is a root, then x minus negative 1 is a factor, and x minus a negative 1 looks like an x plus 1. And then what we end up with down here is going to be one less exponent than what we had there. We had an exponent of x to the third, so that 1 is connected to an x to the second, and then we go down from there, plus 3x minus 6, and then we still have that whole thing is equal to 0, okay, if we're trying to find the zeros. Now, we've gone from a cubic to a quadratic. Now that we have a quadratic inside here, we can use the AC method, or we can use the quadratic formula. Now, if we were to try to use the AC method, then we would find that it's not going to factor, because we would be thinking, what can we multiply to get negative 6 and add to get 3, and there's not going to be one, and so we will have to use the quadratic formula. So we're going to think that A is 1, and B is 3, and C is negative 6, and we're going to plug that into the quadratic formula. X is equal to the opposite of B plus or minus the square root of B squared minus 4 times A times C, all over 2 times A. Plugging in, then, we get x is equal to the opposite of a positive 3, which is a negative 3, plus or minus the square root of b, which was that positive 3 square, minus 4 times my a value of 1, times my c value of negative 6, all over 2 times my a value of 1. Now, to solve, I can do the 3 square, and I can do the multiplication, and I can do this multiplication. So I'm going to have x is equal to negative 3 plus or minus the square root of 9. And then 4 times 1 is 4, and 4 times 6 is 24. There's an odd number, excuse me, there's an even number of negatives. So the answer is positive. All over 2 times 1 is 2. Now we can do the addition. We get x is equal to negative 3 plus or minus square root 33 over 2. And so then we split it into the two possible solutions. X is equal to negative 3 plus square root 33 over 2, or x is equal to negative 3 minus square root 33 over 2. And so we have three solutions. We have x equal negative 1. We have x is equal to negative 3 plus square root 33 over 2. And we have x is equal to negative 3 minus square root 33 over 2. And so we found all of the solutions to that cubic. Any questions on number 20? Excuse me, any questions on number 4 of lesson 20? Okay? All right, that takes us to number 5. Number 5 says find the nth degree polynomial function with real coefficients satisfying the given conditions. Number 5. Here are those given conditions. N is equal to 3. That means it's a third degree polynomial. It's a cubic. Solutions that they give us are negative 5 and 4 plus 3i. They say that those are zeros. That means to us they're zeros, they're solutions, they're roots. and they're saying that the function value at x is 2 is 91, meaning that that's the y when x is 2, 91. Now we want to actually find the equation of the cubic. We know cubic because of that. It's to the third power. It's a third degree polynomial, okay, that has this particular characteristics. Now, again, what this tells me then is this is a third degree polynomial. If the roots are these things, that means that the factors would be x minus those things. So we would have a factor of x minus the first one, x minus the second one, and then there's a little thing that I've got to tell you about, and then that all would be equal to 0. Okay? Now, it would be equal to 0 if we were intending to set it equal to 0. Okay? But what they're really telling us to do is say, let's let the function value at 2 be 91. Okay? So what we're going to do is we're going to say, okay, if we were to later on put a 2 in place of our x's that we've just put on the board, then the answer when you plug in a 2 to all those would be 91. Now, really, what we're going to come up with here is some reduced version of the original equation. In other words, my real equation in blue is the material that I have going on in red times some factor A. And when I do put that factor A in, and then I put the 2 in place of all those x's, that f of x should turn into a 91. Now, our job for a moment is to focus on the red. We want to take the 3 zeros, and you may be thinking, but I only see 2. We're going to take the 3 zeros, and we're going to turn them into a polynomial by multiplying. And then we're going to put the blue stuff back, and then we're going to insert the green stuff, and then we're going to end up with the original equation. You'll see what I'm talking about. Now, here's what you got to know. Irrational roots, square root stuff, comes in pairs. Square root answers come in pairs. Irrational answers come in pairs. Also, imaginary answers also come in pairs. So if you got one, you got the other one. And the pairs that they come in are called binomial conjugates. Excuse me. That means if we have an imaginary root or 0 of 4 plus 3i, there must exist another one that is 4 minus 3i, its conjugate. Now, I'm going to use black to put these numbers in. If there is a 0 of negative 5, then as a factor it would look like x minus negative 5. If there is a factor, a 0 of 4 plus 3i, it would look like x minus 4 plus 3i. And notice I have to put it in parentheses because I'm going to have to distribute that minus sign. And if there exists an imaginary root of 4 plus 3i, then there exists its conjugate 4 minus 3i, which again would have to be put in parentheses so that we could distribute that negative. Now, what we're wanting to do for right now is we're just wanting to kind of leave this a times whatever hanging, and we're wanting to do all of that red stuff. We're going to expand this into a polynomial, knowing that whatever we get may have been reduced by some factor of a. Okay? And we could have even put a big old parenthesis here to consider that we're grouping that. All right, so we got a lot of work to do. We can come down here and scratch that work out to the side. This first little piece is an x plus 5. And that second little piece after we distribute turns into an x minus 4 minus 3i. And that next little piece after we distribute turns into an x minus 4 plus 3i. And we have to multiply all of that. Now you can kind of do it in any order you want. It's not going to matter. But we'll just take this one times all three of those. And then the 5 times all three of those. We'll just multiply the first two first if you like. So we're going to have the x times the first chunk x is x squared. The x times the second chunk negative 4 is negative 4x. The x times the third chunk negative 3i would be negative 3xi. Then we're going to have the 5 times the first chunk x, which would be a 5x. I'm going to put it there by its like term x. And then we're going to have the 5 times the second chunk, negative 4, and 5 times negative 4 is negative 20. I'm just going to stick it down there because there's not another number. And then we take the 5 times the third chunk, negative 3i, and we get negative 15i. And there's not really a deal that looks like it either. And then we combine all of those like terms. We get x squared plus x minus 3xi minus 15i minus 20. Let's say we got that. Now, I'm fixing to move some stuff because I'm not going to have enough board space, you see. So I'm fixing to erase all of the black and blue that you see right above that bottom line. You can rewind if you need to. So we have that answer. Times the little red chunk, the other piece we haven't gotten to yet. And now we've got to distribute all of that. Now, it might be easier to distribute this way, right? The x through all of that. Okay? And so we're going to have x times x squared is x cubed. And then x times x is x squared. And then x times negative 3xi is negative 3x squared I. And I'm not going to draw the arrows anymore. We could go forever, but you can follow along. X times negative 15i is negative 15xi. X times negative 20 is negative 20x. Now we multiply the negative 4 through. Negative 4 times x squared is negative 4x squared. Negative 4 times x is negative 4x. Notice I'm putting my like terms together when I get an answer. Negative 4 times negative 3xi is 12xi. Hunting for a like term to put it with. Negative 4 times negative 15i is positive 60i. I don't have one of those yet. Negative 4 times negative 20 is positive 80, and I don't have one of those yet. Now I'm going to multiply the 3i through. 3i times x is 3xi. 3i times x squared is 3x squared I. There's one of those. That's a positive. 3i times x is 3xi. 3i times negative 15. Let me write this one down. 3i times negative 15 is negative 15i squared. But we know that I squared is negative 1. And negative 15 times negative 1 is positive 15. 3I times negative 15I. Excuse me, I made a mistake. That's supposed to have been a 45. Let me start again. I was really trying not to make a mistake, and I made one there. Um, let's go back to the reds. I missed one. Wow. Wow. Okay, let's start again. We'll do the red. 3I times x squared is 3x squared I. There's that one. 3I times x is 3xi. That's that one. 3I times negative 3I squared would be negative 9xi squared. I squared is negative 1. Negative 1 times negative 9 is 9x. So we have a 9x. And then we have 3I times negative 15I, which would be negative 45I squared. I squared is negative 1. Negative 1 times negative 45 is positive 45, and so we have a positive 45. And then we have 3I times negative 20 is negative 60I. There we go. Notice there's lots of cancellation opportunities. There's a negative 3x squared I and a positive 3x squared I. There's a 2xi, a 12xi plus 3xi, which is a 15xi, and a minus 15xi, which cancels. There's a 60i and a minus 60i that cancels. It simplifies a little bit for us. We end up with x to the third minus 3x squared. We got a minus 24 and a positive 9, which would make a negative 15x. We've got an 80 and a 45, which makes a 125. And so we end up with an x cubed minus 3x squared minus 15x plus 125. That, notice that all those i's canceled out. Now, that was the result of multiplying those three things, those three factors. We multiplied them together. We ended up with this. I'm just going to turn it back into red again. It's going to go right back into here. X cubed minus 3x squared minus 15x plus 125. So what you see in red is a reduced version of that function possibly. It could need to be times 2 or times 3 or times a half or something. Okay? All right, I'm fixing to erase everything underneath. You can rewind if you need to. Let me review what we've done, just in case I may have lost you. That would be understandable. Here's the information they gave us. They gave us that it's a third-degree polynomial, which means it's going to turn into an x cubed when all is said and done. They gave us that the zeros were negative 5 and 4 plus 3i. If that's a 0, then a factor looks like x minus that and x minus that. But an x cubed has 3 factors. They only gave us 2. They only had to give us 2 because imaginaries and square roots come in pairs, and they come in pairs as binomial conjugates. Therefore, if there's a 4 plus 3i factor, then there must be a 4 minus 3i factor, the conjugate of it, which created another factor. Factors are created by x minus roots. What we did at that point then is we said, okay, we're going to take those three factors and we're going to multiply them out to get the polynomial that has those factors. Now, the problem is when you find the factors of a certain polynomial, it's possible that that polynomial could have been reduced by some unknown factor. Example, let me just make something up. If we had f of x is equal to 4x squared plus 2x plus 6, we could change that into f of x is equal to, we could factor out a 2, 2 will go into 4x, 2x squared times, go into 4x squared, 2x squared times, 2 will go into 2x, x times, and 2 will go into 6x, 3 times. And so that 4x squared plus 2x plus 6 could appear by taking its roots as 2x squared plus x plus 3, a reduced version of the original. Now, we don't want the reduced version. We want the original. So we want to try now to find out what factor, that's where A comes in, did this original get reduced by to become what we found. What factor did the original get reduced by to find to end up with what we found? Now, to do that, they had to give us a point. And so they gave us the point F2 equal 91. Now, that's where the green comes in. So we're going to say, okay, when x is 2, the function value is supposed to be 91. So we're putting that 2 in place of x every time. Now, what's going to happen is if we put a 2 in place of x, we may not get a 91. We may get something larger than 91 or smaller than 91. We may have some reduced version. And so what we get when we do this may be the real value reduced by a factor of A. And we want to know what factor of A did this get reduced by so that that became a 91. Or the 91 became that, you see. Okay? All right. So we're going to calculate that and see what it comes out to be. I'll just see if I can do it in my head. We're going to have 2 cubed is 8. 2 squared is 4. 3 fours are 12. 8 minus 4 is negative 4. 15 times 2, negative 15 times 2 is negative 30. Negative 30 and negative 34. Negative 30 and negative 34. We got a negative 34. Negative 34 and 125 is 91. And so we get 91 is equal to the reduction factor times 91. Now, we can solve for A. We're going to undo multiplication by division, and we get A is equal to 1, which means that it didn't really get reduced at all. What we found in pink is the real thing, but it could have been reduced. Now, to get the real one, had A been anything other than 1, then we would have had gone right back to here, and we would take that A of 1 and we would plug it in, like if that had been a 3 or a 4, and we would distribute, and it would make all those numbers bigger by that factor. Well, if we actually plug that 1 in, we're going to have 1 times x cubed is x cubed. 1 times negative 3x squared is negative 3x squared. 1 times negative 15x is negative 15x. 1 times positive 125 is positive 125. So the actual real function is x cubed minus 3x squared minus 15x plus 125. Any questions on number 5? Okay. The next little section is to use the Descartes' rule of signs to determine the possible number of positive and negative real zeros for each given function. Now, the reason we would need that is, remember a while ago, we had this huge list of possible rational roots to choose from, which we said, well, that's better than an infinite list, isn't it? Well, it is better than an infinite list, but notice that some of those were positive, some of those were negative. If we actually had a way to figure out how many of our answer choices were possibly positive and how many of our answer choices were possibly negative, it might make us lean towards choosing from that list positives before we choose from that list negatives and actually getting a hit quicker, okay? Now, you may think in your mind, well, if Descartes' rule of signs takes a lot of time, it might be quicker just to guess. Well, you might be right. But again, every rule in math not only has the value for which it was created, it generally leads to other things, and so it has other values. So we're going to learn the Descartes' rule of signs. There may be times it saves you time. There may be times it wouldn't have saved you time, but it actually gives us some more good lesson and some review of some other mathematics. Okay, the Descartes' rule of signs, question number 6. Now, here's the actual function, and we'll talk about the rule in a minute. We have f of x is equal to x cubed plus 2x squared plus 5x plus 4. Now, what we want to do is find the sign changes. Find these sign changes. The sign of the first term is positive. The sign of the second term is positive. The sign of the third term is positive. The sign of the fourth term is positive. There are 0 sign changes. It went from positive to positive. That's not a sign change. Positive, positive, that's not a sign change. Positive to positive, that's not a sign change. There are 0 sign changes. Therefore, there are 0 possible positive real rational roots. Okay? Now I need to say something to you here. We just found out how many possible positives there are. There's 0 possible positives. That's what we were looking for. Now here's the thing. Remember that rational roots, that's the ones that are not irrational. Remember that irrational roots and imaginary roots come in pairs. That means we're going to lose 2 at a time. Because when we lose something that's not rational, it's either irrational or imaginary, and you don't just lose one rational at a time or one imaginary at a time. You lose them 2 at a time because they come in pairs. So if there had actually been 4 sign changes, we would have said there's 4 or 2 less than that, because we'd lose either 2 rationals or 2 irrationals too, or 2 less than that, 0 possible positive real rational roots. If we had ended up with 6 sign changes, we'd say there's 6 or 2 less than that, 4 or 2 less than that, 2 or 2 less than that, 0 possible positive real rational roots. Okay? So there's going to be that number, or start losing it in groups of 2. Okay? Possible positive real rational roots. That's how you find the possible positive real rational roots. To find the possible negative real rational roots, we're going to look at f negative x, which means that everywhere that there's an x, we're going to replace it with a negative x and look at our signs and determine the sign changes in that scenario. Now, we're going to have f negative x is equal to, when you take a negative number raised to the third, you get a negative number. When you take a negative number squared, you get a positive number. A negative times a positive is a negative number. And so we're using sign rules to find out the final sign. And so we replaced x with negative x, created a new function, and then we're going to look at the signs. The sign of the first one is negative. The sign of the second one is positive. The sign of the third one is negative. The sign of the fourth one is positive. When we look at sign changes, there's 1, 2, 3 sign changes. Now remember that rational roots come in pairs. Remember that irrational or imaginary roots come in pairs. So if we lose something that's not rational, we're going to lose its partner also. So we're going to lose in groups of 3. There's 3 sign changes, which means there are 3 or 2 less than that 1 possible let me write my whole sentence. There are 3 sign changes. Therefore, there are 3 or, drop out 2, 1 possible negative real rational roots. There are 3 or 1 possible negative real rational roots. Now, that tells me that there's 0 possible positives. So if I was going to choose from a list of roots that I had found by using the rational root theorem, and there's a bunch of positives and negatives, would you start by choosing a positive 1 or 2? No, because there's 0 possible positives. Why waste all your time with synthetic division on positive choices when you know that there's not any of them that's going to work? Now, there's possibly 3 of the negatives that would work. So we're going to decide in our synthetic division choices of a 0 to plug in, we're going to plug in a negative choice, you see. Everybody see how the Descartes' rule of signs can help us in making better choices from our list of possible rational roots. Okay? You may say, well, what did you want for an answer? I want this sentence, and I want this sentence. And I wanted to see the work here where you plugged in negative x so that you could determine how many possible negative real rational roots there were. Okay? All right, any questions there? Okay, number 7. Number 7, we have f of x is equal to 5x cubed minus 3x squared plus 3x minus 1. And we will use Descartes' rule of signs to find the number of possible positive real rational roots and the number of possible negative real rational roots. So we look at it as is and find the signs of each term. We have a positive, a negative, a positive, a negative, and we determine the number of sign changes. There are 1, 2, 3 sign changes. We're in their original function, so we're talking about possible positives. So we say there are 3 sign changes. Therefore, there are 3, or remember we lose them in groups of 2, so 2 less than 3 is 1. 3 are 1 possible positive real rational roots. Okay? To find the possible negative real rational roots, we find f negative x and look at the sign changes. So everywhere we see an x, we're going to plug a negative x. And we're going to get our signs right. When you take a negative raised to an odd exponent, you get a negative. When you take a negative raised to an even exponent, you get a positive. That positive times a negative gives you a negative. A positive times a negative is a negative. And so the result is this. We're going to identify our signs. We have a negative, a negative, a negative, a negative. There's no sign change, no sign change, no sign change. There are 0 sign changes. Therefore, there are 0 or 2 less than that, which you're not going to have a negative number of something, you see. I'm having trouble spelling that 0 on it. Therefore, there are 0 possible negative, and I could have caps locked that like I did the positive just to focus on it. There are 0 possible negative real rational roots. So here's your answers. We found the number of possible positive real rational roots and the number of possible negative real rational roots using Descartes' rule of signs. Any questions on number 6 and 7, Descartes' rule of signs? All right, I'm going to stop right there and then do one more video for 8 and 9, and that'll keep the videos a little bit shorter. We're already 44 minutes and something in. All right.